This is a presentation of the University of Wisconsin Parkside.
I'd like to take a little bit of time introducing our speaker for tonight. Dr. Shea got his BS degree from UW-Madison, so he, in a certain sense, is a native Wisconsinite. Am I correct?
Definitely.
And he got his PhD in Illinois. There's might be some resentment here, but nonetheless, he got his degree from University of Illinois, Champaign-Urbana. He worked as a geologist in Texaco in the Gulf Coast for a fairly long time at the beginning of his career. And then he also served for quite a few years, 26 years, as the editor of the journal Geoscience Education. He has been in retirement for quite some time now, but still showing up at the science night for quite a few years now. And so last semester he volunteered to give this talk tonight.
Thank you, Dr. Pham. And good evening, ladies and gentlemen. Our topic for this evening is fracking, specifically hydraulic fracturing of rock, and to a lesser extent, directional drilling. We'll cover both of those briefly. I want to talk briefly about the origin and accumulation of oil. The first step in the formation of oil and natural gas is the growth of quintillions of microscopic organisms in the ocean. These organisms live at various levels in the ocean. They live and die, and when they die, their bodies fall to the bottom and accumulate there if conditions are right, if there's not too much oxygen and they decompose. Under the right conditions, many, many feet of these organisms may accumulate. Eventually, the organisms, the bodies of all these organisms form a black carbonaceous mud. And perhaps eventually that mud will get buried. It'll get buried by more mud, perhaps, and then additional sediment. And it may get buried by thousands of feet of sediment, as a matter of fact. And this burial carries with it certain conditions. As the sediment gets buried deeper and deeper, the pressure goes up, as you can imagine, and the temperature goes up. And if the temperature gets high enough, up to perhaps a few hundred degrees, and the pressure stays up, the bodies of these marine organisms are transformed into oil and natural gas. Natural gas if the temperature gets fairly high. And this gas occurs in the tiny pores of the sediment in which it originally accumulated. Now, on some occasions, this oil and natural gas may simply be trapped in this sediment and stay there. It may stay there for millions of years. On other occasions, the oil and gas may get squeezed out of the sediment, the rock. The rock becomes a shale. The oil and natural gas may get squeezed out of the sediment into other nearby rocks. And if that other rock is permeable, that is, if the oil and natural gas can flow through it, the oil can move. Now, almost invariably, these rocks are saturated with water. The pores are filled with water, seawater typically. And since oil and natural gas are less dense than water, they float on the water, and they float upward even within the sediment, even within the tiny pores of the sediment. This slide shows a typical, almost a classic anticlinal fold in which oil and gas can accumulate. What happens is, perhaps the oil and natural gas formed in a layer like this one here, say, and then it gets squeezed out of this rock and gets into this layer here, which is permeable, and it floats upward on the water. This is water saturated, flows upward until it encounters another impermeable layer, in which case it may flow upward on the bottom of this layer right here to the top of this structure where it will accumulate. In this case, what's happened is natural gas has accumulated here. This would be natural gas, and oil here, and then water down here. Then an oil company, if they're good enough, may come along, drill down into the oil, and the pressure of the gas will force some of this oil up the drill string to the surface where it can be collected and then carted off to be refined and used. Eventually, in a field such as this, the oil rig would have to have a pump would be installed, and the oil would be pumped out. Now, this is the way oil and natural gas were produced for perhaps 150 years, from 1859, up until about 2000. This is a typical, almost a classic trap. There are lots of different kinds of traps, but this one is fairly typical. But in some cases, as I said earlier, the oil and natural gas may be trapped within the rock in which they formed, and they can't get out because the rock isn't permeable. The oil is trapped in there and can't get out. And geologists have known for a long, long time that there were formations where this oil and natural gas had accumulated in rock, but it was inaccessible. There was no way to get it out. So it just stayed there. And then through time, the oil companies and the drilling companies and the federal government devoted lots of time and money to developing ways to get that oil out. The oil companies invested big money in it, and the federal government invested big money in it, billions of dollars in the form of grants and tax relief. And eventually, they developed two techniques that allowed this oil to be extracted: fracking and directional drilling. Fracking is a technique used for drilling and producing petroleum that involves injecting water and other fluids and a proppant, I'll explain what that is, like silica sand, at very high pressure, perhaps in excess of 10,000 pounds per square inch, high pressure, into rock at depth to increase permeability. And the way it does that is it fractures the rock, it cracks it, it creates openings through which the oil and natural gas can flow. But they had to have a way to hold the fractures open, otherwise they would just close down when the pressure was released. And that's the function of the sand. The sand grains get in these cracks, and when the pressure is released, the sand grains prop open the fissures that the oil can move through, hence the term proppant. Horizontal drilling, or directional drilling, consists of several techniques for drilling non-vertical holes for extracting oil and gas. This slide illustrates two wells that show the differences between the old methods of extracting oil and the new. In the old days, way back when I was an oil geologist, most of the holes we drilled were vertical or near vertical. There wasn't much directional drilling of any kind. And there wasn't much fracking either. So a well would be drilled down, and it would, if it passed through a formation like the one I've been talking about, they couldn't get the oil. They had no way of getting the oil out. But then these two new techniques were developed. And the way that works is that a hole would be drilled vertical for several thousand feet if the rock was at that depth, if the formation was at that depth. A hole would be drilled down, and then it would be turned. They developed techniques for drilling directionally off to the side and turning the well and making it horizontal, as illustrated here. And if they were good at it, the hole would penetrate the potential producing formation, and they could drill right through it. The record for drilling such wells is 7 miles of horizontal drilling. 7 miles. An amazing thing that they were able to do that. One of the ways they were able to do that is they developed ways of having the drilling mud turn the drill bit like a turbine. And that way they didn't have to turn the whole drill string, which made it a lot less expensive, and they could turn sharper corners. The next step after having drilled a well such as that would be to put explosives down here and blast holes in the drill string. And then the fracking fluid would be pumped down under very high pressure. It would go through the holes in the drill string, penetrate the rock, and under these very high pressures, it would cause the rock to fracture. And this fracturing would open channels so that the oil and natural gas could flow into the drill string and up and be produced. You can see the point here. This well here doesn't come in contact with very much of the producing formation, so even if you fracked it, you're just not involving much rock. But if you can drill horizontally, you can bring your drill bit or your drill string into contact with lots and lots of rock, and thus the well can produce more oil and gas. So these two techniques, horizontal drilling and fracking, were developed over many years, and they were finally perfected right about the year 2000. This diagram, which you probably can't see very well, I'm sorry to say, is a little bit better pictorial representation of a horizontal well. You can see the drill string up at the drill rig up at the top there, drilled down perhaps several thousand feet, maybe in excess of 10 or 15,000 feet. Turn the well or the drill bit or the drill string horizontal, and stay in the potentially productive formation. Frack the well, and then you can pump out the oil. It's a very, it's a time-consuming technique, and it's very expensive to do, and it requires millions of gallons of water and tens of thousands of gallons of fracking fluid, and we'll talk in considerable detail about that. Now, what are the advantages of fracking? Why is it being used? Why is it such a big deal? Well, the first thing is that fracking has allowed the extraction of very large amounts of otherwise unproducible oil and natural gas. Before fracking and horizontal drilling, this oil simply wasn't producible. And I'll show you some of the places where this is taking place. This is the United States, Florida, Maine, Washington, California. One of the really big plays, an area where lots of wells are being drilled, is called a play. That's an industry term. One of the big plays, big fracking plays into tight shale is the Bakken Formation of North Dakota, Montana, and adjacent areas of Canada. And this play is extremely active, as we'll see in just a minute. Some of the other big plays, and incidentally, these shaded areas are the areas where oil, gas, and coal are produced in large parts of North America. Some of the other big plays are the Barnett Shale, Texas. I'll show you a map of that. The Eagle Ford play in southwestern Texas here, which I'll show you a map of. The Fayetteville area here, the Haynesville, Bossier. And another of the biggest ones is the Marcellus Shale play in West Virginia, Kentucky, Ohio, Pennsylvania, and parts of southern New York State, although at the moment, New York has a ban on fracking, so there's no production in New York. And Governor Cuomo has various state agencies working to determine whether they should allow fracking, because, as we'll see, there are problems. Now, the Marcellus is a really big play, and I'll show you a map of that in just a minute. Oh, I did it again. This didn't have any effect. Oh, now this is interesting. You can watch the growth of drilling. Every new dot that appears is a new well, and just watch over here. You'll see them start here. The date is up here, and the production is here. It's really low. It's less than 100,000 barrels a day here. Now, you see it start up here, and look at the wells increase in number over here. Now it'll start over here. hundreds of wells are being drilled as we speak. I mean, this is one of the biggest oil, the Bakken is primarily an oil play. And the amount of drilling going on there is absolutely fantastic. The unemployment rate, in North Dakota is approaching zero, and their economy is booming. But we'll see that it's not all a bed of roses. This is a map showing the Barnett Shale play in Texas. This is the Red River, the boundary between Texas and Oklahoma. Dallas County here, so Dallas would be about here. Fort Worth is right over here somewhere. And you can see there's just an intense amount of drilling. The blue dots, let's see, they'd be oil. Usually they use green, but it's blue on here. And the red are gas. So the Barnett is both an oil and a gas play. And Texas laws are so favorable to drilling that lots and lots of wells are drilled right in the city of Fort Worth, right in residential areas, industrial areas, near schools, near stores. It's just an absolute boom there. This map shows the Eagle Ford play of Texas, southwest Texas. Here's an index map. The red dots are gas wells. The green, which you probably can barely see, are oil wells. And it doesn't look so active, but this is a very active play too. And the nice thing about this area is all the infrastructure, pipelines, railroads, what have you, is already there. So it's very easy to get this oil to market. And the gas too, because the pipelines are there. In North Dakota, it's much more difficult because the pipelines, the railroads and so forth are not really there. The next play is the Marcellus play of the eastern United States. This sort of rectangular area here is Pennsylvania, as you might guess. And over here would be West Virginia, Ohio, and up here, southern New York. This is a really big area, and it's primarily a gas play. This shows the colors on here show the depths, starting out at less than 2,000 feet, way up there at the upper left, and going down to below 9,000 feet. Right here is a spot that's below 9,000 feet. I guess some of this other purple is 9,000 feet too. So it's really deep here, although oil wells can go down to at least 30,000 feet, but they don't have to do that here. So that's one of the advantages. And let me show you what this has meant for oil production. This graph shows the oil production in North Dakota. And the black line is goes through the actual points, whereas the red line is a trend line. Production was increasing slowly and reached, 150,000 barrels a day at one point, and then it began to drop off. And then fracking began in the late 90s here. And production increased slowly, and then the fracking boom really caught on, and the production has shot up. It's probably reached 500,000 barrels a day by now. Production in North Dakota has become, I think, the second largest producing state in the country now. The prognosticators have made some interesting predictions about what's going to happen to U.S. oil production. You may be aware that U.S. oil production reached its peak in 1970, and that was at about 10 million barrels a day, which is this horizontal line right here. That's where it is. That was back in 1970, which would be over here. This is now, by the way, 2012. And you can see the experts are predicting that the boom in fracking, because of the boom in fracking, U.S. oil production is going to go up, up, up. Now, you can't pay too much attention to the slope of these lines, but I just wanted to indicate that the prediction is that U.S. oil production will go up. It will exceed the 1970 peak, which nobody expected, and it will even exceed U.S. consumption. The red line is U.S. oil consumption, and at some time out in perhaps 2025 or so, we can't be sure when, U.S. oil production will exceed U.S. oil consumption. Again, a situation that nobody expected, and a situation that lots of people are very happy about. It's even expected that the U.S. will become, if I recall correctly, the second leading oil producer in the world, which again, nobody really expected. And this has huge implications for our economy, for unemployment, balance of payments, and lots of other things. But as I said, we'll see that it's not all a bed of roses. The boom in fracking has even had a big effect in Wisconsin, because it turns out that Wisconsin has large areas of exposures of sand which is ideal for fracking. The Cambrian sandstones of Wisconsin, Cambrian and Ordovician sandstones of Wisconsin are either near the surface or at the surface in this orange area all along here. Right at the moment, there are 16 active sand mines in Wisconsin, shown by the green dots. There are 11 new sand mines that are already in development, and there are an additional 14 that are planned. And this really is a sand mining boom for Wisconsin. Counties in western Wisconsin now are having trouble keeping their highway employees because they can get better paying jobs working in the sand mines. This dark slide here is an aerial photograph of a sand mine in western Wisconsin. You can see it's quite a big operation. Oh yes, here's a truck right here. The actual production is mostly concentrated out here. It's piled up, and then apparently they bring it in and they move it by pipeline to the processing plant here, where they wash it and sort it and get it ready for use. And then they take it by conveyor belt to this building here, where it's loaded into trucks. The trucks go over and get on this road right here, obviously, and they haul it off to railroad yards, where the sand is carted off to the oil fields. This is a big deal for Wisconsin. There are some problems with this sand mining, and the biggest problem is, although the truck traffic on county roads that weren't really designed for those trucks is one of the problems. It's costing the state and the counties a lot of money, but silica dust is a big problem. Silica dust is dangerous. If you breathe too much of it, you get a disease called silicosis. You get this silicate in your lungs, and it can be debilitating or, in some cases, fatal. And you can see that the mining itself generates dust, and the truck traffic on the roads over here generates dust, and the truck drivers and the equipment operators inhale this stuff. They should be wearing masks, but they usually don't do it. Now, we just gave one answer to the question, why is fracking important? The second reason fracking is important is that it has resulted in numerous environmental problems. And here's why. Something like in excess of 99% of the material injected into fracking wells consists of sand and water, quartz sand and water, and that stuff is not much of a problem, obviously. But 0.5% on that order, depending on the well, something like 0.5% of the material injected into the well consists of a veritable witch's brew of chemicals, and I'll show you some of them in just a sec. 0.5% doesn't sound like very much, does it? But if you're pumping in, say, 8 or 10 million gallons of water, then 0.5% amounts to a substantial amount of water and various chemicals. Now, what are those chemicals and what are they used for? Well, this slide gives you some notion, although only a limited notion. Some of it is acid to help open channels in the sand or in the rock. Some, they inject friction reducers, gelling agents, I really don't know why, scale inhibitors, and lots of others. And One toxicologist, a very famous woman, I can't remember where she's from, I remember her first name was Theo, she kept a list of the various fracking chemicals, and she came up with over 600 chemicals that were being injected into wells. Now, and the oil companies insist that there's no way that these chemicals could get out, that they're deep down in the ground and they're not going to get out, but that's a fairy tale. Here's some of them: acetylenic alcohol, ethylhexanol, monoethanolamine, let's see, acetic acid, ethyl mercaptan, you can imagine that's a bad smeller, toluene, acrolein, ethylbenzene, naphtha, acrylamide, boric acid, ammonia, ammonium chloride, ammonium nitrate, iron, benzoyl chloride, blah, 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 cadmium, diesel 2, chlorine, ethylene glycol, formaldehyde, kerosene, formic acid, fuel oil number 2, hydrogen sulfide, nickel sulfate, isobutyl alcohol, methanol, naphthalene, xylene, styrene, sulfur dioxide, benzene, sulfuric acid, and triethylene glycol, just a few. And if that doesn't sound nasty to you, you don't know much about organic chemistry. Because many of these materials, very many of these materials, have very deleterious effects on human health. And this is, again, a very short list of just a few chemicals and their effects. If there's an X in this column, then this chemical affects the skin and eyes, the lungs, the gastrointestinal tract and liver, the nervous system and the brain, the immune system, the kidneys, the cardiovascular system, the developmental cycle in humans, the reproductive organs, and the endocrine system. And some of them are carcinogens and mutagens. And you can see there are lots of X's here, right? And, this one here is interesting. Various other complex organic chemicals, and they affect every one of these systems. Actually, I was interested to see that methanol, which is simply wood alcohol, was listed here as affecting every one of these. Well, it isn't a carcinogen, apparently, thank God, huh? But affects all of these systems. Well, I won't bother with that. So, there's lots of really nasty chemicals. Now, the question is, can they escape the wells? Well, yes, they can. They can get into aquifers and, in fact, reach the surface. And sometimes they flow back out and are evaporated into the air, as we'll see. This up here lists some of the effects, but methane gas contamination in drinking water was 17 times higher near fracking sites. I'll show you that. Toxic wastewater, often radioactive, is stored in open pits. We'll see that. 60% of oil wells leak over a 30-year period. Toxic fluids seeping up along the drill pipe and in natural and artificial fractures can reach aquifers in as little as 3 years. And 30 to 70% of the fracking fluid is brought back to the surface when the pressure is released and oil or natural gas is being produced. The fracking water, 30 to 70% of it comes back to the surface and has to be disposed of. And what they do is they dump it into pits, as we'll see. Here's a woman, her home was in Pennsylvania. Here's her house. She had a very good water well. She got nice, pure, clean drinking water. Then wells were drilled near her property, and this is what her drinking water drinks now. And even with this bad slide, I don't think most of you would want to drink that water. And actually, what you can see is not the worst of it, right? What you're seeing is the sediment mostly. But if you were to open up and smell it, then you'd get an idea of all the junk that's in there. The well is totally unusable. I mean, you wouldn't want to drink that or cook with it or take a bath in it, would you? I don't think so. And that's not an exaggeration. There are lots and lots of home water systems that have had exactly this effect. And they've had another effect which is not so charming. This dim slide shows a man he lives near Fort Lupton, Colorado, which is in northeastern Colorado. And there's so much methane in his tap water that you can light it on fire. And that's what he's doing there. He's holding a cigarette lighter, cigarette lighter, and it's burning, and he turned on the tap, and nothing happened for a while, and then poof, it burst into flame. And there are many, many examples of such things. And of course, if your well is contaminated, you're pretty much out of luck, right? But all you can do is, and the drilling companies have had to pay for this in some cases, you have to have water trucked in big tanks. And that's expensive and really frustrating when you had a good well at first. Here's a humorous cartoon from a Pennsylvania newspaper. Free gasoline straight from the tap. Showering every Pennsylvanian with unexpected bounty. Lovely. And turning every home into a potential gas station. Gas, $3.99 a gallon. Yeah, well, that's a bit of an exaggeration, but not much. Now, this slide shows a drilling site, an operational drill site, and it illustrates a number of things. First of all, this is a pretty good-sized site, and it makes quite a mess, doesn't it? Trucks coming in, and every single fracking well requires several hundred truckloads of materials. Not just the water, although that's the biggest traffic, but all this drill pipe, all this equipment, the drill rig, it requires literally hundreds of truckloads, and these trucks are driving back on, narrow country roads that weren't built to take this kind of traffic. Here are the pits I was telling you about and that were mentioned. This is probably drilling mud here. When you drill a well, you need drilling mud to lubricate the drill bit as it goes down, to cool it and lubricate it. This pit here contains fracking water, probably fracking water that is produced water that was brought to the surface when the well was producing oil and or natural gas. And what the drillers would really like is for this stuff to just evaporate. And in fact, what they do sometimes is set up pumping systems that spray the water into the air and let it fall back into the pool to increase the rate of evaporation. Well, where does that stuff go? It goes into the air, and it's probably heavier than air, so it sort of flows along the surface. And one of the characteristics of the air near drilling wells is the stench. Ammonia, just any number of chemicals, because they're all in there. This is a photograph of an anti-fracking rally in Albany, near New York. These people want to convince the governor not to allow fracking in New York. Let's see here. In fact, this map shows areas, the colored areas here are areas that have either enacted a ban on fracking, local areas have either enacted a ban on fracking or have a temporary moratorium on fracking or are considering a moratorium. Probably state law is going to override these laws anyway, but perhaps not. I'm not a lawyer, so I really don't know. Now, one of the most problematical aspects of fracking is the following. Back in 2005, when Vice President Cheney convened his energy group to give advice to President Bush, they persuaded Congress and the President to enact a law that exempts drilling and oil companies from the provisions of the National Environmental Policy Act of 1969, the Safe Drinking Water Act of 1974, the Resource Conservation and Recovery Act of 1976, the Superfund Act of 1980, the Toxic Release Inventory of 1986, and the Clean Air Act of 1990, and others. These companies are exempt from the provisions of those laws, which frankly to me seems absolutely outrageous. They are working with all of these toxic and carcinogenic chemicals, and they're just completely uncontrolled. And that leads to consequences, as I'll show you. This is Jackie Schilke. Jackie Schilke and her husband bought a ranch near Williston, North Dakota in 2001. It had been their lifelong dream to own a cattle ranch. And they bought this ranch and they were raising Black Angus cattle. And here's another thing, they don't own the mineral rights to their land. So, I think it was in 2006, the drillers moved in. This is in the Bakken area of North Dakota, which I was telling you about earlier. The drillers came in and they started drilling, and the shillings, the first thing they noticed was the smell. They noticed an ammonia smell right away, very strong. Then their dog died. Then their cattle began to get ill, and interestingly, the back half of their tails fell off of a lot of them. Not a particularly horrible thing, but not very nice. And it illustrates that something was very definitely wrong with their metabolism. And then some of the cattle died, and they dropped their calves early, and the calves were dead. They didn't survive. And then I want to give you the details on this. Mrs. Schilke got sick. She got arsenic poisoning. They later determined that she had arsenic poisoning. It probably came from the clay that was used to line the pits to prevent seepage. Then the North Dakota Health Department found ethylene dichloride, a probable carcinogen, in their water. They wanted the North Dakota Health Department to test their air, but they wouldn't do it for some reason. So they hired a private firm. They found benzene, toluene, and methane in their air 24 hours a day. These are very nasty substances. Now, the result of all this, and the Schilkes are getting nothing out of this. They don't own the mineral rights, so they get no royalties. And they can't say anything about the drilling, where it is, and, well, they just have no control over it whatsoever. The drilling companies come in and they just do their thing. So the Schilkes are stuck. They bought this ranch. They can't produce cattle because they won't, they're good people. They won't sell their cattle because they know they're poisoned. So they can't make a living anymore. They basically can't live in their house because of the water and air pollution. And both of them are sick. Mrs. Schilke in particular is extremely sick. And they can't sell their place because of the environmental contamination. So the Schilkes are absolutely stuck. I don't know what they're going to do. Now, another example of the kind of thing that can happen. In March of 2011 in Greene County, Pennsylvania, a man named Robert Allen Shipman and his company were charged with illegally dumping millions of gallons of natural gas drilling wastewater in 6 counties in Pennsylvania. 98 criminal counts were filed against Shipman himself. 77 charges were levied against his company. Dunkard Creek, into which they dumped some of this stuff, had a huge fish kill. In fact, more than a fish kill. Virtually everything in Dunkard Creek for a stretch of something like 25 miles was killed. And Dunkard Creek is a tributary of the Monongahela River, which joins the Allegheny at Pittsburgh and forms the Ohio, right? And people, municipalities downstream get their drinking water from the Monongahela. And it was terribly contaminated. Shipman was convicted, and his company was convicted, but nobody went to jail. The local citizens were outraged, but nobody went to jail. Another problem. Let me see if that slide is due up. The oil companies the drilling companies are supposed to dispose of this wastewater, either by taking it to a sewage treatment plant, but the sewage treatment plants aren't set up to process this water, or they could take it to what's called an injection well, where they can basically pump or dump the stuff deep underground. And oh yes, this is the slide I was looking for. This map shows the location of injection wells in Ohio. Most of them are in eastern Ohio. But you can see there are lots of them, and they're scattered all over the place. And what these companies can do, remember, they're exempt from all the laws. They can just dump whatever they want to into these injection wells and pump it deep underground, and the idea is out of sight, out of mind. At one stage in this fracking boom, a company was injecting fracking well wastewater into an injection well at Rosharon, Texas. I think that's a corruption of Rose of Sharon. Okay, Rosharon, Texas. Now the papers they were carrying said that this was just salt water. A highly unlikely circumstances if you have fracking water, right? And they pulled up to this well, and they had it rigged, so they were just letting the water flow by gravity into the well. Apparently that worked with this well. And they left the engines on their trucks running. Unfortunately, the wastewater contained all kinds of volatile organic chemicals. It was sucked in by the engines started to race. One of them backfired, and what do you suppose happened? A big explosion and a fire, and 2 drivers were killed. It's been estimated that there are something like 650,000 injection wells in the United States. Now, not all of them are active, but there are lots of them. They're everywhere, and it's permissible just to dump this stuff in or inject it, and like I say, out of sight, out of mind, right? But interestingly enough, that turns out not to be the case, because the stuff leaks back to the surface if it's under high pressure. It leaks back onto the surface. It gets out of the well, reaches the surface. It's terrible stuff. It may cause earthquakes. That was kind of funny. Recently in Ohio and Oklahoma, a series of earthquakes was clearly caused by this injection. This was kind of curious to me, because when we lived in Colorado for a time, there was an episode of an injection well at the Rocky Mountain Arsenal in Denver that was producing earthquakes. And well, for a long time, the earthquakes started happening, and nobody knew what would cause this. Now, geologically, that makes no sense at all for earthquakes to just start up in a region. So a consulting geologist named Dave Evans dug into the matter a little bit, and he found that it was due to this injection well. When they stopped pumping the stuff into the injection well, the earthquakes gradually tapered off, and they didn't occur again. But what they were injecting was chemical warfare agents, chemical warfare materials. Now, for a long time, they used to just dump this stuff in ponds at the surface, and that ought to sound familiar. But then there were objections because ducks would land in it and die, and nobody likes that, right? So they thought they'd pump it into the subsurface. They were down 10 or 12,000 feet, and they thought, no problem. But then these earthquakes began to happen, and one of them had a magnitude of 5.3, which was noticeable. And so people were extremely worried about it. So they, of course, denied it. When Evans first suggested this, they saw this was nonsense. But then it became clear that he was absolutely right. And that's what is the response of the drilling companies when somebody says, your drilling contaminated the water in my well with either methane or with this or that chemical, and I want you to do something about it. And they said, their response is, well, prove it. And how do you prove it? I mean, it's extremely difficult. And you don't have unlimited funds if you're a homeowner. So the gas companies insist, the drillers insist, that there's been no contamination of water wells with fracking fluid, but that's just absolute nonsense. It happens quite regularly. We can see 2 reasons why fracking is important here. The third reason is that fracking has increased the supply of fossil fuel and delayed the adoption of alternative forms of energy and thereby seriously worsened the problem of global warming. All of a sudden, we have lots more oil and natural gas to produce. It's available, it's there. The oil companies want us to burn it, right? I mean, that's what they're all about. Let me just show you the problem. You probably know this, so I won't dwell on this too long. But this graph shows the increase in the carbon dioxide concentration of the atmosphere from 1958 back here up until 2012. And it goes from, perhaps 320, 315 parts per million to very nearly 400. In fact, it's likely that it's clear, it's not likely, it's clear that we will reach 400 parts per million within 2 or 3 years. You watch the figures, you'll see that that is going to happen. The black line is the actual observations, the red is a trend line. Now, is this a problem? Well, this graph shows the carbon dioxide content of the atmosphere back into geologic time. This is now, this vertical line is now, 2012. Back to 420,000 years ago, okay? Now, how could we possibly know the composition back then? Well, it comes from, the current measurements are made at Mauna Loa volcano by the Scripps Institution of Oceanography. The old measurements come from gas bubbles from the ice core that the Russians drilled at Lake Vostok in Antarctica. They drilled down, and the layers can be dated, and the gas bubble, you can capture the gas from the bubbles and measure the carbon dioxide content. They've gotten to be very good at that. These are very reliable. Well, you can see that through most of those 420,000 years, in fact, through that whole period, the carbon dioxide content of the atmosphere, I guess you probably can't tell, but this is 300 parts per million right here, this line. It just reached it here. Other than that, it didn't even reach 300 parts per million until the carbon dioxide content began to go up during the Industrial Revolution. And the modern measurements start right here. And the reason this line is vertical, whereas on the other graph it was sloping, is that the time scale is so expanded. This is now, and this is 50,000 years ago. So the period of 50 years hardly shows up on any, in any horizontal direction here. The graph is nearly vertical. And you can see that the rate of increase here is just very, very fast. In fact, I looked up the numbers. I had the numbers, not just the graph, and I figured that the rate of CO2 increase during the last 50 years has been 136 times as great as the fastest rate of increase during the last 420,000 years. A horrible thing. Now, but what does that mean to the temperature? Well, what's happened is that this is a graph of global temperature. The black are the actual observations year by year. The red is a 10-year running average. And what's happened is the global temperatures have increased regularly up through the end of World War II. Then they declined for a while, and then they started up again, and they just keep going up and up and up. The average global temperature, based on the 10-year running average, has increased 1.7 degrees F in 100 years, from minus 0.65 up to 1.04 up there. So global temperature is being seriously affected by this carbon dioxide, and fracking is going to allow us to produce more and more carbon dioxide. When I went into looking into this topic, I really didn't have any strong feelings one way or another. But after investigating the situation, I've concluded that fracking causes way too much serious environmental damage, and it's seriously worsening global warming. There are only two possible things we can do, really. We've got to either much more tightly control fracking. We've got to have controls on the use of these chemicals, and we simply can't allow unlimited production of gas. Or perhaps we may have to simply prohibit fracking to stop the production of this additional fossil fuel and the additional carbon dioxide that's being injected into the atmosphere. Thank you.